All right, so today we're going to be looking at topics 1.11 and 1.12. The big idea being that you have to rewrite or move the function in every form, whether it's standard form or factored form, reveals something different. Okay, so here's like the gist of the key topics that we're going to be going over today. And just move on now. All right, topic 1.11. The factored form reveals the zeros of the x-intercepts and the holes and vertical asymptotes for rationals. So for example, on this graph, the factored form is going to be x squared plus 3x plus... Actually, this graph isn't factorable, but if we're looking at x squared minus 4 over x squared minus 5x plus 6, then, okay, let's look at this right now, right? So what does the standard form tell us? That's what we're going to look at first, and then factor form after. So standard form reveals end behavior from the leading term and the y-intercept, which is the constant term. Okay, so how do we find the end behavior from this? The end behavior is always just going to be the horizontal asymptote. So we look at the degrees of the leading co and then the leading coefficient. So the degree is going to be 2 and 2. So the degree is the same. So therefore, on the top and bottom, we do the numerator, the leading coefficient of the numerator divided by the leading coefficient of the denominator. So this is 1x squared and 1x squared. So 1 over 1. So our horizontal asymptote is going to be 1 over 1, which is 1. So our end behavior is going to be as x approaches infinity, y approaches 1, and as x approaches negative infinity, y approaches 1. Now, how do we find the y-intercept from this? Okay, x squared minus 4, x squared minus 5x plus 6. So as we know, the y-intercept is just when x equals 0, right? So let's just put 0 for all the places x over here. So 0x squared minus 4 is negative 4, so negative 4 is on the top. And then 0 here, let me erase this one thing before. So 0x squared on the top minus 4. And then on the bottom, it's going to be 0 squared minus 5 times 0, which is just 0, plus 6. So the y-intercept for this graph is going to be negative 4 over 6, which is negative 2 over 3. So therefore, from the standard form, we can find the end behavior, which is going to be, since the same degree on top and bottom, and 1 over 1, it's going to be 1. And then we can find our y-intercept, which is going to be negative 2 over 3. Now, what can we find from the factored form? Let's look at that. The factor form is going to tell us the zeros and the holes and the vertical asymptotes. So looking at what standard form and factor form gives us. Standard form gives us end behavior, EB, since it gives us the horizontal asymptote, and it gives us the y-intercept. I'm just going to write y in for now. Okay, now let's look at the factored form of this equation. So if we factor on top and bottom, the top is difference of squares, so it's x minus 2 times x plus 2. And then the bottom is going to be x minus 2 times x minus 3. So I hope you guys all saw how that factors out. Negative 2 times negative 3 equals 6, and then negative 2x plus negative 3x is negative 5x. So factors out. Now we can clearly see our holes, vertical asymptotes, and zeros here. So our hole, okay, so x minus 2 cancels out. And where does x minus 2 equal 0? When x equals 2. So one of our holes is going to be at x equals 2. And then to find the y value of that hole, we're just going to plug in x. So 2 plus 2 is 4. 2 minus 3 is negative 3. So it becomes The whole is at 2, and then 2, so 4 over -1, which is -4. So we're gonna have our whole at 2 comma -4, which it was pretty easy to find uh once we put it in the factored form, which is what the factored form tells us. And the other two things the factored form tells us is the x-intercept and vertical asymptote. So vertical asymptote is going to be at x equals 3, since that's what's left in the denominator. And what makes x minus 3 equal to 0? It's when x equals 3. So that's going to be our vertical asymptote. Vertical asymptote. And our 0 is going to be at x equals -2, since that's what makes the top 0. X equals -2. Okay, so quick summary of what we just went over there for those of you who joined a little bit late is the standard form tells us this is the standard form, right? Here, let me erase the one in on the top about this. Okay, so this is the standard form, right? This reveals us the end behavior, which reveals us the horizontal, which is revealed to us by the horizontal asymptote. So the horizontal asymptote of this is 1, which we can see clearly in standard form. And that means that as x approaches infinity, y equals 1, and x approaches -infinity, y equals 1. And then it also reveals to us the y-intercept. So we just plug in 0 for all areas of x. So that becomes -4 over 6, which is -2 over 3. Which is the y-intercept, so 0, 2 over 3. And then we just saw how the factored form gives us the not the y-intercept, the x-intercepts or zeros, the vertical asymptotes, and the wholes. Okay, now let's look at binomial theorem. It's pretty cool. And actually, before binomial theorem, I'm going to do one quick review on slant asymptotes. So over here, x squared plus 3x plus 5 over x plus 1. To find the end behavior of this, we know that when the top degree is greater than the bottom degree, so 2 is greater than 1, uh, it's a slant asymptote. So, and how we do that is the long division. So x squared plus 3x plus 5 being divided by x plus 1. So first thing we do, x times what equals x squared, since we have to subtract by whatever we're getting. So x times x equals x squared. So x times x, and then we have to multiply that to the whole thing of x plus 1. So x squared plus x. So we have x squared plus 3x plus 5, and we're subtracting x squared plus x from that, which gives us 2x plus 5. And now we look at what times x equals 2x, which is going to be 2. So we're doing x plus 2. Then we subtract, so 2x plus 2. And then we have 3. And 3 is going to be our remainder because x times anything, it can't like equal 3 unless you're doing like divided by 1 over x or something like that. And we don't want to get into that. So our quotient or like our actual like answer is going to be x plus 2, which is going to be our slant asymptote, and our remainder is going to be 3. Now, let's look at binomial theorem. Okay, so binomial theorem is, or wait, that's the wrong spot. Yeah, there. Okay. Binomial theorem is basically a way of quickly expanding equations in larger degrees. So for example, with binomial theorem, you'll be able to quickly expand x plus 4, let's say x plus 4 to the power of 4. You'll be able to quickly expand that. So let's look at how that works. So the first thing we're going to look at with that is Pascal's triangle. So Pascal, I'm just going to draw a triangle. Triangle. Okay, so let's look at a polynomial with degree 0, which is just going to be like 1. We're going to start out like that, right? And then and then to build our triangle, we're going to add 1 on both sides. So 1, 1. So this is polynomial of degree 1, right? I'm going to have the degrees over here. So 0, then 1. So what that means is this equation could be like x plus 1 to the power of 1, which is just x plus 1, right? 1 and 1. Now let's look at degree 2. Then we add 1 on both sides. And then here, we add these two terms to get what's in the middle of the two of them, which is going to be 2 and 1. And I'm pretty sure all of you guys know this. It's just the basic like sum of squares rule, which is x plus y squared equals x squared plus 2xy plus y squared. So if using Pascal's triangle, we can find the coefficients that come in the front of these terms. So here it's 1, here it's 2, and here it's 1 again, which follows Pascal's triangle when it's degree 2, right? So x plus 1 squared, using that theorem, we can see the coefficient of the first one is going to be 1, then 2 times x, and then 1 again. Now, I want you guys to notice a pattern here. When we're doing x plus y squared, the first term is going to be x squared because it's x times x, right? And then what happens after that? The degree of x is going to decrease. So then it becomes x to the 1 times y to the 1. And then we add our leading coefficient, the coefficient, which comes from Pascal's triangle, 2. And then we do y squared. So really, using Pascal's triangle, we can find like any like x plus 4 to the fourth. You can do this pretty quickly. And I'll show you guys how to in a second. But first, here's the pattern. So like it's x squared times y to the 0 plus 2, because we get this number 2, 2x1 times y1, and then plus y squared x to the 0. And since anything to the power of 0 is just 1, we can like erase these, the x to the 0 and y to the 0. And from that, we get x squared plus 2xy plus y squared. So any questions on how we're getting that right there? All right, now let's move on to degree 3. So use the same pattern. Add 1 on the outside, and then 1 plus 2. We're going to add those two together to get 3, and then 2 plus 1, 3, and then we're going to add 1 on this side too. So this is going to be our coefficients for some type of equation to the power of 3. So I'm going to give you guys an example and do it with you guys now. Okay, so let's look at, actually, let's just keep it simple. We'll do x plus y cubed so that you can see the things. Okay, x plus y cubed. Okay, first term, we're going to have just our first term to the power of 3, x to the third, times y to the 0. Okay, so if you notice another pattern here, always the two terms, they're going to add up to the total degree. So x to the 3 plus y to the 0. So like 3 plus 0 equals 3, right? And then we have our next term. This time, first, let's add our leading thing from Pascal's triangle, 3. And then we reduce x, this is degree, by 1. So 3x squared. And then we increase y by 1, y to the 1. Again, the degree of x is 2, the degree of y is 1, so 2 plus 1 equals 3. So it's following that pattern. Then, again, we look at the triangle, so 3, so 3, and then this time we put x, and then x to the 1, and then y to the 2. We're decreasing x by 1 and increasing y by 2. Y by 1, so increasing y by 1 from the previous term. And then, finally, we have our last term, which is just the leading thing is going to be 1, so we don't even have to write that. It becomes x to the 0, y cubed. Okay, cool. Now, we know that y to the 0, all these are just going to be 1, so we can just write x cubed, and then plus, okay, this x squared, and then y to the 1 is just y, so we can write just y, then plus 3x to the 1 is just x, so x, y squared plus y cubed. Okay, so you guys see that? See how we get that from Pascal's triangle? Now I'm gonna do one final problem of x plus 4 to the fourth, and then I'll give you guys some problems to work on. Okay, so x plus 4 to the fourth. First, let's expand Pascal's triangle one more time. Degree is 4 now. So remember, as we're increasing in degrees, we just go 1 on the outside, and then we add these two terms, so it's 1 plus 3, 4. Then what's between these two terms? We have to add the two terms, so 3 plus 3, 6, and then 3 plus 1, 4. And then again, can't forget we have to add 1 on the outside. So these are going to be our coefficients for x plus 4 to the fourth, or any polynomial, like anything like in the form of a plus b, which is any two numbers or variables to the fourth. So now let's look at x plus 4 to the fourth. First, our first term is just going to be x to the fourth, right? Simple enough with just 1. And then we have to add a 4 at the start. 4 times, and we reduce x by 1, so 4x cubed. And we increase the degree 4 by 1, so times 4, right? Because now it's 4 to the 1. Then it becomes 6, and then we reduce x by 1. X to the third becomes x squared. And 4 to the 1 becomes 4 to the 2. So 4 to the 2, which is just 16, but I'll write 4 to the 2 so you guys can see it clearly. Then we have 4 times x. It's just x now, but now it's 4 cubed. And then finally, plus it's just 1 plus 1. No, we didn't have to write that one. 4 to the 4. Now let's multiply this out. So first term is just x to the fourth. It's not being multiplied by anything. Then next term, we have a 4 times 4 here. So it's going to be 4 squared. So it's 16x cubed plus, and then we have 6 times 4 squared. So that's 6 times 16, which is 96. So 96x squared. And then 4 times 4 cubed, which is 64 times 4, which is 256. So 256x. And that's because 4 cubed is going to be 4 times 4, which is 16. Again, times 4 again, so 64. And then we multiply by that 4, so 256, 256x. And then plus 4 to the power of 4, which is again 4 times 4 times 4 times 4, which is 256. So just like that, this big like x plus 4 to the fourth, which normally if you had to just like multiply x plus 4 times x plus 4, and if you have to do that 4 times, that would take you so long, right? You'd have to manually multiply every term out and then add the terms up, and that would just take a long time. But with Pascal's triangle, we just did that huge like x plus 4 to the fourth in maybe a minute, right? So now I'm going to give you guys a question on this. Here's an example question. What use does this, good question, what use does this theorem have besides time? Well, the main use is time pretty much, because if you think about it, these are like pretty simple, right? But if I ever ask you to do like x plus 3 to the power of 8, it would take you incredibly long to like, it would be x plus 3 times x plus 3 times x plus 3. And think about it, you get like 3x squared, and then later you'd get like, let's say 7x squared and then 10x squared, and you have to add all of these and you have to multiply all of them. It would take so incredibly long. And with this triangle, you can just do it faster. And if on pre-cal test, they're gonna give you like multiple of these questions where it's like x plus 2 to the fourth, and then it's gonna just if you manually do each one, it's gonna take you too much time and not gonna be able to finish the test on time. So these are like similar examples to what we already went over, so I'm going to skip them. So here's three questions for you guys to answer, which is over the two things that went over so far. So using division, give the slant asymptote. So slant, that's what I'm asking for here. Asymptote. And then over here, just expand uh, these two equations. So I'll give you guys some time to do that. Okay, so first, slant asymptote for this equation. So 3x squared minus 2x plus 4. Okay, so, and then we're dividing it by x minus 1. So first, we have to look at what times x equals 3x squared, which is going to be 3x. 3x times 3x, I mean 3x times x equals 3x squared. So then we have to multiply 3x to the whole thing. So 3x times 3x is 3x squared. And then 3x times negative 1 is negative 3x. And you have to remember that we're subtracting these terms. So 3x squared minus 3x squared, so these two cancel out. And then negative 2x minus negative 3x is the same as negative 2x plus 3x, which is just x. And then we bring down the 4. So x plus 4, bringing down this 4. And then x times what equals x, which is going to be 1. So 3x plus 1, and we're subtracting x minus 1, which is just going to leave a remainder of 5. And then, but we don't need the remainder, and we're looking for slant asymptote. It's just whatever is over here. So our slant asymptote is going to be 3x plus 1. Okay, now let's look at, I'll solve, let me erase this. Now I'll solve 2x minus 1 cubed minus 1 cubed. Okay, there's something interesting when there's a negative number on the second term. So first, let's go from the top. First, we're going to do 2x. Let's just organize our thing. 2x cubed. Oh yeah, let me write down Pascal's triangle as well. So 1, 1, 1, 1, 2, 1, and then 1, 3, 3, 1. So the degree is 3, so this is going to be our thing, 1, 3, 3, 1. Oh yeah, cool. So first term is just, we just 1. And then remember, this is going to be negative 1 to 0, so we can just ignore it. And then we do plus, we reduce 2x, the degree of 2x by 1, so 2x squared times negative 1, and then that's to the power of 1, so we can just leave that. And then remember the 3 in the front. We can't forget that. And then we're going to add 3 in the front. Again, these are Pascal's triangle. And we have 2x, and then negative 1 squared, and then finally plus negative 1 cubed. Okay, so first, 2x to the third. That means we have to put 2 to the third and x to the third. So 2 to the third is 2 times 2 times 2, which is 8. So 8x cubed is going to be our first term. Then we have 3 times 2x squared times negative 1. So first of all, this whole term is going to be negative because it's the rest of the thing is positive, and then this is just negative. So we're going to do minus, and then 2x squared is just 4x squared, and 4 squared times 3 is 12x squared, so minus 12x squared. And then we're going to do negative 1 squared is just 1, so we can ignore that, right? Then it's just plus 3 times 2x, just 6x, so plus 6x. and then plus negative 1 cubed. Negative 1 cubed is negative 1 times negative 1 times negative 1, which is negative 1. Okay, so this is going to be our answer to the first problem. So, and also a pattern here, when the second term is negative, or even if it was the first term negative and the second term positive, it's always going to be like alternating between positive and negative. So, as you can see here, it's 8x cubed positive minus 12x squared plus 6x minus 1. So, it's alternating between plus and minus because whenever you put a negative number to a even power like 2 or 4, it's going to equal the positive value, so 1. Whereas if you put negative 1 to the power of 1, it's just negative 1, or 3, it's also negative 1. Because if you think about it, negative 1 times negative 1, which is negative 1 squared, equals 1, right? But that times negative 1 equals negative 1, which is what negative 1 cubed is. Now, let's look at the last question on this batch, x plus 3 to the fourth. All right, I'm going to go on this one a little faster since we do have to get to the next topic soon. But understanding binomial theorem well is pretty important, so it's time well spent. Okay, x plus 3 to the fourth. And okay, so it's going to be, remember the previous one was 1 for Pascal's triangle, it's 1, 3, 3, 1. So we add a 1. So 1, 4, 6, 4, 1. This is for degree 4. So first term, x to the fourth, and then plus, it's going to be 3 to the 1 times x cubed 6 times, and then 3 cubed is 9 times x squared plus 4 times 3 cubed is 27 times x, then finally plus 3 to the fourth. So now let's multiply this out. We're going to get x to the fourth plus 3 times 4 is 12, so 12x cubed. And then 6 times 9, 54, plus 54x squared. And 4 times 27 is going to be 108. So 108x plus 3 to the fourth is 3 times 3 times 3 times 3, which is also 108. No, sorry, it's 81. Yeah. Okay, so that's going to be our answer for the second problem. Any questions on either of those problems? All right, sounds good. Now let's move on to transformations. So this is something that you guys probably worked on in algebra 2. So basically, we're just looking at how graphs shift when you're transforming them, right? So let's look at the base graph like this. This is a quadratic graph, right? A times B times x minus h squared plus k. Okay, so as you guys may know, everything inside the parentheses is going to horizontally change the graph. So x minus h is going to be how much x shifts like left or right. So if h is 3, then it shifts right 3. So h equals horizontal shift. For horizontal, I'm just going to write hors, and then shift. Now, B is going to be horizontal stretch. B equals horizontal stretch or compression. So for example, and if B is 2, then we're multiplying like the graph of x by 1/2. So everything inside the parentheses does the opposite. So even on h, if you think about it, normally when you subtract 3, it's like going down or going left, right? But since it's inside the parentheses, you're actually going right, which is the opposite. In B, normally if B was 2, then it would be stretching the graph and making it wider. But since uh everything's opposite inside the parentheses, if b was 2, then it would really be multiplying the graph by like a vertical shift of 1/2. So it's actually getting tighter. So it's horizontally compressing is what's happening. And then a is going to be a vertical stretch, which just if a is 3, then for let's say on a graph where it's going up 1 and up 1 y value for every x value, if it was multiplied by a vertical stretch of 3, then it would go up 3 for every x value goes up 1, if that makes sense. And then k is the vertical shift. So shift. So it's making it go up or down. And let's take a look at this graph. X minus 3 squared plus 1. So the original graph is this, right? On this graph, our vertex is at 0, 0, but here, x minus 3, that's our h value, right? So minus 3, normally minus seems like left, but since it's in the parentheses, we're going right. So going right 3, so 0, 0, right 3, and then plus 1 is just up 1, so plus 1. So it goes from 0, 0, and then since we're adding 3 to that, so 0 plus 3 becomes our x value, and then 0 plus 1 becomes our y value. So our new vertex is at 3, 1. Okay, now let's look at some more examples. And okay, here's another thing. Negatives. So if you see a negative on outside the function, then it's a vertical reflection. So what that means is you're reflecting the graph over the x-axis. So for example, if we look at this graph, and let's say this is x squared, right? Let's say we're going from x squared to negative x squared. I'm going to draw negative x squared in a different color, blue. So we're going to reflect it over the x-axis, and it's going to become this. Because this point is going here, this point going here. It's just reflecting over the x-axis, right? All these points are just, and whenever it's just a vertical reflection, to find it, each point we can look, let's say the original point is x comma y, then the new point is going to be, after a vertical reflection, it's going to be x comma negative y. You guys understand that? Because it's it's basically just flipping over the x-axis. So y becomes negative y. And then here we have it inside the function. So like this would be like negative x minus 2 squared, for example. Then we flip it over to x-axis. So which means x comma y would go to negative x comma y. Okay, now let's actually look at the graphs. So negative f of x plus 2. And f of x equals x squared, right? Now, let me erase this extra stuff now. Okay, f of x equals x squared. So now let's plug in x squared for where f of x is. So since it's negative f of x plus 2, this becomes negative x squared plus 2. And right away, I can look at this and see that our vertex is at 0, 2 because it's not being horizontally shifted and it's going up 2. And this is actually vertex form, which tells us our vertex. Okay, so we can tell that our vertex is at 0, 2, and then we can tell it's a negative graph, so it's being reflected over the x-axis. So what would have normally been this? If it was just x squared plus 2, it would have been this. But no, actually, sorry. I forgot to tell you guys that before any translations, first comes the reflections and stretches and shrinks. So here it would first go like this. It would become a graph like that. And then after you shift it up to, then it goes like that. Now let's look at this example. Okay. F of negative x, and f of x equals square root of x. So so they're saying g of x equals f of negative x. So f of negative x. And since f of x equals square root x, we're just going to put root, and then, no, sorry, we're going to put, since it's f of negative x, we're going to put negative, and then we're going to replace the x with what that is. So it's going to be root of negative. Sorry, it's going to be negative f of x, which is negative root x. So for example, if x was 4, then it would be 2, negative 2. It would go like this. Okay. Now it's your turn. Okay. So here's the parent graph. It's just this, right? And just looking at this graph, you can tell that this is an absolute value graph, but you don't even need that part. Starting from f of x equals x squared. So actually, I don't know why they're giving you this graph. Let's look at here. F of x equals x squared. So x squared. Write g, which is reflected over the x-axis and shifted right 1 and up 3. So if f of x equals x squared, then how would I write g of x, which is f of x after it's been shifted right 1. So I'll give you guys the things. Right 1, and it says it here, but it's kind of in bad quality. Up 3, and reflected over the x-axis. So reflect over x-axis. Oh yeah. Yeah, that's correct. Pause it. I'm going to explain this question now. Okay, so first we looked at our original graph is x squared. Okay, good. Now we reflect this over the x-axis. So what we're doing to f of x becomes negative f of x, right? And then we notice that we're going right 1, so it becomes negative f of negative, no, sorry, x minus 1, and then up 3, so plus 3. Okay, so this graph, now let's plug in f of x for what it is, right? F of x is x squared, so we're going to get negative, and then x minus 1, since x minus 1 is inside the parentheses of f of x, that's going to go in where x is. So we're substituting x minus 1 for what x is. So right now, x is just x squared. Now we're going to make it x minus 1 squared. And then the stuff outside the parentheses remains the same. So our new graph is going to be negative x minus 1 squared plus 3. Now, one of your guys' answers was negative x squared minus 1. plus 3. And the thing about this is a different graph, right? This is basically saying since x is already squared there, this is the same as saying negative x squared. And then you're just doing minus 1 plus 3. So it's just negative x squared plus 2. And then now it's a completely different graph, right? And like, it's not the same. So that's why like when you're doing these transformations, when you're doing right, like f of x minus 1, that goes inside the parentheses, and you have to make sure that you replace what x is there. So x gets replaced by x minus 1, and that whole thing becomes squared. Okay, now describe the transformation of 3f of x minus 1. And then what does this have, this affect, how does this affect the domain and range of this function? And remember, f of x equals x squared. All right, I'll give you guys like 1 minute to solve this question. I'm gonna solve this question in 3, 2, 1. So 3f of x minus 3. Sorry, not 1. Okay, so what's this doing? We're shifting it right by 3. So I'm gonna write that R3. And then we're doing a vertical stretch. So vertical stretch by 3. Okay, so f of x is originally gonna be this, right? And the domain is originally negative infinity to infinity, and the range is originally 0 to infinity. So R equals and D equals. Now, if we're doing a vertical stretch by 3, then this graph just becomes sharper, right? It changes from this into the new graph I'm going to draw in blue. It'll be something like that. So that doesn't actually change the vertex point. So our range is going to remain the same. And our domain also, it's still technically going to negative infinity and infinity. It's just like sharper right now. So it'll technically go slower, but since infinity and negative infinity don't work like that, it's like still the same time. So then we shift it right. So it actually becomes a graph like this. So again, it's sharper, but the range doesn't change from this. The vertex point only shifted right. So the domain is still negative infinity to infinity, and the range is still 0 to infinity. So this has no effect on the range. And the transformations for this we're going to describe is vertical shift by 3, and that's because 3 is on the outside of like the function of f of x. And then shifting right 3, because that's inside the parentheses of f of x. And with that, that covers all of topics 1.11 and 1.12. And let me know if you guys have any questions, and I'll be happy to answer.